Okay, good thing I was only muted on the Zoom recording for the first 40 minutes. So super helpful. Sorry everyone online, my bad. Oh, it's recording nothing for 40 minutes. Oh, my bad. On last Tuesday, I also didn't record the screen. So turns out that's not my job. Not very good at it. So better at other things. Okay, sorry, click in if you have a yeah, one giant breath and silent in the room. I swear to God I turned it on. I don't know. Okay. Is that it? Everyone wanted to vote? There's a tiny bit of movement. Not that much movement. Okay, there's some questions that I think we're going to answer probably. First question is, does infrared light become permanently trapped by greenhouse gases or does it escape? That's going to be the first thing that we're going to answer. Then we're going to ask questions about how the ozone hole was created and how it creates like differences for us living on Earth. And of course, the question here is this part of the natural cycle? So are ozone holes natural? We're going to talk about Earth's surface and atmospheric gases, how they absorb energy and how they give it back off. And then, is heat transferred through circulation of greenhouse gases? Is that how it gets out? Okay. So let's have a look at this picture. The effects of the atmosphere. Okay. I know these are very advanced drawings. So visible sunlight comes in from the left. The sun's over here. And we have all our favorite processes. You have emission from the sun, goes through, transmits through the atmosphere. Some of it gets absorbed in the atmosphere. So examples would be like infrared gets absorbed at the top. We saw that in the telescopes. Ultraviolet gets absorbed by ozone, right? And then visible makes it all the way down to the surface. Some of it gets scattered. That's why the sky is blue. And it's not blue on the whole planet, right? This isn't a natural property. So if I were to draw this properly, there should be like a line here. This is the night side, this is the day side. And the blue should only be on the left side. But of course, black on black is really hard to see the difference. Okay, on the night side, you don't have any light anymore, ostensibly. Let's say the moon is not visible. And so infrared light just gets out, right? Some of it gets out. Some of it's absorbed. That makes like a nice warm summer night. A hot surface stays hot. Anyone here live in the desert? Okay. You may notice that in the desert, it gets cooler faster at night. Why is that? What? Warm bodies of water. Warm bodies of water help, but that's not what's helping the atmosphere stay warm. Warm bodies of water do what? We started class thinking about this. They have energy to give, that's true. Warm bodies of water evaporate. And they put water vapor into the air. And water vapor is a greenhouse gas that likes to trap infrared radiation. So if you have no bodies of water, it's probably dry in the desert, right? Real dry, right? Great for your skin. And so as soon as the sun goes down, the infrared light can get out very easily. As opposed to by the beach, where it might be very humid, it gets trapped, it stays warm. Do we see the difference? So it's not just the body of water, it's the water vapor in the air. Okay? So that's a version here, scattering, bounces around and then we absorb it and we're like, oh, it's hot. Okay. And this picture here, of course, we can convert to our favorite picture. You know, to grow in love, right? Oh, not another one of these. Okay, so here you have the thermal emission from the sun is the dashed line. And we can think through all the processes, right? So this object does not bring off a lot, not give off a lot of blue. So here, green and red, this is probably an orange object. This is the energy in. Notice that this is the stuff that was coming from the sun, and this is the stuff reflected. The difference is how much energy you have available, right? So if you're, I don't know, rich grandfather gives you $1,000 to go to the World Series game, right? And you find tickets cheaper, you get to pocket the difference. So you have this budget to start with, right? And you only need to use this, and this is what you have left over, right? And that leftover can be used to heat your home. That's a bad analogy. I don't know. I tried. But you get the idea. The idea? Okay, all right. So this is the energy in, right? And when you look at a diagram like this is not what we mean by red, green, blue, right? So if, for example, the thing is more blue, right, that means this is where the reflection peaks, in this peak here, versus energy out. Energy out's way down over here. I can't see it good, not a snake, right? If it were warmer, this comes to the left. Okay. If it's hotter, colder, it goes to the right. Good. So we're going to talk about weather and climate, how the atmosphere, we already talked about how atmosphere gains energy from light, and we talked about the rotation. So now we want to think not just about how things happen on a day-to-day basis, but remember we said the word climate is historical weather patterns, understanding yearly variations and understanding, say, thousands, millions, even billions of years of weather, right? So one thing that we want to understand is where do you get atmosphere from and how could you possibly lose it? Okay. And can we use any sort of theories to understand Mars and Venus? Right? So the major question here on the left-hand side, this is not a real photo. This is an artist's conception. Left is real Mars, right? What Mars might have looked like. So for example, we saw that it had evidence of water on the surface. We saw erosion features. So there must have been running water. Did it have lakes? It has clouds now. Did it have like thunder clouds? The green? I don't think they took the artist's, what is it called? Never mind. Okay, so where does atmosphere come from? What are the sources of atmosphere? Outgas. Good, that's a good one. Sure, yeah, like we grab stuff, right? And then like if you have a lot of gravity, you can hold on to your atmosphere more. Sure. Yeah.
Evaporation and sublimation.
Evaporation and sublimation, right? So if I have an ice cap and I evaporate it, then it becomes gas that I can breathe. Yeah. Yeah. Okay, interesting. All right. Not on Venus and Mars, but we'll get to that on Earth for sure. Yeah. Okay, so I didn't include that. I'll do 4 in really, really small letters, plants and animals for Earth only. Okay. So here are the major sources. Evaporation, sublimation, outgassing. These are the 2 major ones. But some of the ways we get it is through impacts. So whether that's stuff smashing into the surface, like meteors, asteroids, comets, you can deliver gas that way. You can also get particles hitting the surface and they leave energy, they deposit their things there. Outgassing, the 2 dominant gases you get are water and CO2. And those are the gases that are trapped in with the magma. There is some nitrogen and there is some sulfur. Sulfur is what gives it the awful smell. And like mining, you can like go down like, volcanic vents, like seep sulfur, pick it up, it's super toxic. That's like what goes into all of your electronics. Evaporation, sublimation, lakes. Talk about it. Okay. Okay. Oops, this has been going for a long time. So why didn't Earth outgas as much CO2 as Venus? Is it because Earth didn't have as many volcanoes? B, volcanism was only active for a short period of time on Earth. C, Earth outgassed CO2, escaped the gravitational pull of the Earth. D, Earth's CO2 never made it out of the mantle. Or E, none of the above, it did outgas it. Okay, everyone's voted. 5, 4, 3, 2, 1. Okay, interesting, interesting. Okay. I think most of you will be surprised to learn that Earth did outgas as much. Sometimes it's okay to picky, I mean, of course, we should read ahead and then we come informed and we can ask questions. But you're like, I don't know. It's definitely not E. He never tricks us, right? Okay, so that's a little weird because we are obviously very different from Venus. The first thing you ask is, did Earth have as many volcanoes? Yeah, probably. In fact, we are larger than Venus is. And historically, we were talking about the fact that larger planets hold on to their heat better. And so that means they have more volcanism. So we, in fact, have more volcanism than Venus. So that's not true. This is definitely not true for the same reason, right? Volcanism is ongoing today. A form of volcanism is this that mid-Atlantic ridge where we're creating new crust currently at the bottom of the mid-Atlantic Ocean, right? Some CO2 does escape, but not very much. Very, very little when it gets broken down. You don't know that, but it's fine. And this one here, we get lots of CO2 out of the net, but something else happens that saves us. Okay. So here's an example of outgassing. Happens all the time. Anyone know what that is? Where it is, maybe? Yeah, Big Depression, that's a pretty good guess. It's the thing I'm asking about is this. This is a version of outgassing. If I were to stand near it, it would stink. No, that would be great because I just talked about those. But you can go, you shouldn't. This is Yellowstone. And so Yellowstone has geothermal vents. And so material from the mantle, it's like sitting right underneath the crust, and then liquid makes its way down, seeps in, it's heated, comes through. Those are geysers. But sometimes you just have pockets of like gas that are coming out of the ground itself, and they just like steam the whole time, and it's all like smells like stuff because it's sulfur, right? And sulfur smells like rotten eggs. So if you stand downwind of it for a long time, all your clothes smell like rotten eggs. Yeah. Okay. So we outgas a lot constantly. Like these things are just going and going and going, adding atmosphere. But this isn't the whole story, right? We have to think about the entire cycle of what happens to these gases. So what are the sinks? Well, I'm just going to tell you these. We're not going to go into them in detail. There's two ways for to lose it. Most of the atmosphere from the top of the atmosphere boils off. Something called thermal escape. Okay, here. Some of it participates in chemical reactions. So for example, if you leave a piece of metal in water for a long time, what happens? It rusts. So oxygen that's in the water finds the metal and it forms something called rust, and it changes the color. And you get little spots, orange spots. Okay, that's something called oxidizing. Or it might get cold and you might take the atmosphere and you might condense it into an ice, right? Or you might condense it into a liquid, right? Okay. So let's have a look at how these sources and sinks happened at Mars and Venus, and then we'll think about the differences that let us exist here on Earth. The Earth one is a lot longer. Let's start with Mars. I can't read that. What does it say? Oh yeah. This is about 0.6% of Earth's atmospheric pressure. That's a really thin atmosphere. Almost all CO2. So you'd think, oh, that's great for greenhouse gases, but it's freezing, really, really cold. So in fact, the polar cap, which is shown here, this is, I shouldn't have covered up the scale. This is hundreds of kilometers wide, and it's all frozen CO2. If you've never seen frozen CO2 before, think dry ice. So next time you have a party and you throw dry ice into your drink, that's the same thing that this is made of, identical. Okay? So Mars is so cold that carbon dioxide can freeze out naturally and form on the surface. There's the sunset on Mars, I promised you. Kind of bluish, a little bluish pink, maybe. Mars has very little atmosphere. The sunsets suck, right? And that's just because there's no scatter. Like if you think about us going to the moon, there'd be no atmosphere to scatter. It'd be light and then dark. So a thin atmosphere is light, a little bit of, right? Okay. So let's talk about what happened on Mars. In the first 1 to 2 billion years, it was really warm. Like nice, that pea just came out, still hot from the oven, okay? And then you had like tectonics, you had volcanoes. This is when you get Olympus Mons, right? And you have lots of outgassing, so it's replenishing the atmosphere. And you probably warmed the planet up enough for liquid water. Questions about oceans, questions about life. We're gonna avoid some of those right now. We'll come back to them later maybe. But you definitely had erosion. You saw all of this evidence for erosion, right? So you had temperatures and pressures that were enough for water to flow on the surface, right? And then Mars cools down. Why does Mars cool down? Faster than the Earth? You want to talk to them? Yeah. That is certainly the loss process that gets rid of the heat. That's correct. But why does the interior compare to the
That seems to be too big.
Yeah, so we're still thinking about the biggest level. I'm talking, what it, there's this giant planet, right, like the Earth, warm inside. Mars was warm for just 1 or 2 billion years and then got cold. Why?
It's too much.
Okay, let's go back to this analogy. How does size affect heat? Yeah,
It's just a lot smaller.
smaller. So if you have a potato and a pea, I'm not a fan with the food, right? Potato and a pea, which one cools down faster? The pea. So why did Mars only stay warm for the first 2 billion years? All time. That's like as simple as they can make it, right? That's the answer. Now, the ways in which it lost heat are very complicated, right? Like how did that heat get to the surface? How did the infrared escape? What are the processes that stopped it or slowed it down? But the basic answer is straightforward. It was small. Okay. So here's what happens. As it cools off, it starts to lose its magnetic field. The atmosphere starts to get stripped away. The cold interior means you don't have volcanoes, means you don't have outgases. But once you start losing it from the top, there's nothing replacing it from below, right? No atmosphere means that those solar UVs and those X-rays, they're just heating up the surface even more. Now, Mars is farther away from us, but its surface through this process is probably heating up, right? The H2O gets broken apart. The H is very light, it escapes. And the O that's left around literally rusts the surface. Have you ever wondered why Mars is red? Just think that the whole planet has rusted. Okay, and this is a way to take atmosphere and put it into the surface. Is that a question?
Yeah, it's like oxygen, the molecule by itself rusts.
Well, not by itself. It participates in chemistry. It's called oxidation, where you take oxygen and then you take it from a gas form, you add it into a solid, and it changes it. I'm calling it rusting for support. That makes sense? Orange Mars is rusted. Okay. And now you have less atmosphere, you have less greenhouse effect. So the surface gets colder in some places, and those gases freeze out. Now you have a real problem, because once you have frozen the atmosphere out, you cannot warm it back up again, because now it's all condensed and it's very reflective. Snow is super reflective. So now it's not getting absorbed by the surface and it's just reflecting back into space. So that source of heat, the sun, is not contributing to your surface. And so your atmosphere is permanently collapsed. Yeah. This is a very good question. Very good question. We're finding out. I cannot answer it today. It's a very good question. It's one of ongoing research. This is how you lose the ability to support water on the surface. And the diagram looks like this. Early Mars probably had I don't know if it had oceans, but definitely like lakes and stuff and streams and probably a nice magnetic field and volcanoes, and all that just shuts off. And then all of these loss processes get worse and worse and worse. The planet's surface gets colder and colder and colder. The atmosphere collapses. And now you can't live. That makes sense? Okay. Let's talk about Venus really quickly. Venus is crazy. Okay. Venus is 90 times the pressure at Earth's surface. So this is primarily CO2. You can't breathe even if you wanted to. That's what it looks like from the surface. The temperature is 880 degrees Fahrenheit. So all electronics fail. Like the longest that we've had something sit on the surface, I think is 45 minutes. Or it completely melted, just would send out pings of data. This is a black and white image. I can bring a color image if folks really want to see, but it's bad. You know, it's just yellow, it's sulfur. And we want to understand, how did our nearest neighbor, Venus, become a hellscape, right? So we might have a little bit of vested interest in this because, like, we really like not living in a place that looks like that, right? So what is the difference here? Venus is smaller, right? So it's not how many volcanoes they have. Something else happened, okay? So we're going to describe something called feedback. Now, feedback is not just what I give you, like, oh, you're doing great, right? That's a version of feedback. Feedback is also a physical process. And you can have two versions. You can have positive feedback, you can have negative feedback. Positive feedback doesn't mean it's good. Positive feedback means you're going to create the same behavior. Okay, so the example I like to use here, put a ball on a hill and then kick it. Rolls downhill, right? Okay, this is an example of unstable or positive feedback. The change, the small kick, gets amplified by the fact that the hill is curved. As opposed to if I sit at the top of a half pipe and I kick the ball, it will, get down all the way to the bottom, but then it'll stay there. And now if I walk down to the bottom and I kick it at the bottom, it'll just return to where it was, the bottom of the half pipe, right? This is negative feedback, the change being counteracted by the system. Does that make sense? Negative feedback, not always bad. Just means that whatever you were trying to do was thwarted, right? Here, it was amplified. Negated, negative, positive, amplified. Cool. Okay. Clouds are an example of feedback. Told you I hate clouds, but we're going to talk about clouds more. So here's Earth's clouds. Let's say we increase the clouds. What changes? So now new clouds trap more infrared radiation. The troposphere, the bottom layer, the one that's closest to us, gets warmer. That creates additional evaporation, which makes more clouds. Right? Okay, that's a positive feedback example. Now with clouds, I can do the same thing. Because clouds are so annoying, they can be a source of positive or negative feedback. So here's them being negative feedback. Okay, so these new clouds, let's say they're not near the ocean. Let's say they're over the desert somewhere. Okay, these reflect the light. That means there's less available at the surface to form, new clouds. So the troposphere cools, and you don't get any new evaporation, and then the clouds dissipate. So you might have, say, a little pond or something, create some clouds, and then they reflect light, and it cools that area, and the clouds. This is a negative feedback. Positive feedback, negative. Bad examples or okay? Okay. All right. It's got a picture of a cow. You can't hate it. Which of the following is an example of negative feedback? A, a spooked cow causes a stampede. B, the hotter you get, the more you sweat. C, ice melts, making the surface darker and therefore warmer, causing more ice to melt. D, the rate at which the balance in an interest earning savings account increases with time.
Can you?
Yeah.
Can you explain it one more time? I don't think I did.
Well, we're gonna find out.
Thought I understood it. I don't understand.
Yeah.
I love that you already jumped in. Why do you ask a neighbor who doesn't have the same answer? Because of the 4 answers, they're about even. Okay, click in if you got it. Anyone change their mind?
That's true.
Okay, so what is feedback? What? It's a result. It's something about the result, right? Yeah. Well, that's like how I would ask for feedback. But in a system like this, when we talk about positive or negative feedback, right? Well, let's think about negative feedback does what to the system? Causes it to grow in the same direction or contract? Contract. So whatever change you were trying to affect, it stops that effect. Okay. Positive feedback is a runaway process. So whatever change you were trying to affect gets easier to do or just takes on a life of its own. Okay. So let's think about this one here. A spooked cow causes a stampede. Positive or negative? Positive. Not a good thing to have happen to you, but cows scare other cows, which scare other cows, causing a stampede. Positive feedback. Okay. Next one. Do people know what an interest earning savings account is? Okay, this is where you put your money in and then your money makes more money, right? I know, crazy concept. Okay, so the rate at which the balance goes up, how much money you have, the pot of money, and they keep adding more money, is positive. That's a good one. That's a good one and a positive.
Yeah.
Okay. Ice melting, making the surface darker, which makes more ice melt. Good or bad? Bad. Positive or negative? Positive, because the heating caused more heating. Okay, the hotter you get, the more you sweat. Why negative? Yeah, this is the only negative feedback example up here. Okay, wait, you're not done. You're not done. You're not done. Okay, first you have to learn about Venus. You're not done learning about Venus. Okay. So the question is it a sister planet or is it an evil twin? Okay, it's as large as Earth, right? It had outgassing, it had volcanism, right? Plenty of greenhouse gases. It was big. It held on to its atmosphere. Okay. This led to greenhouse effect, led to high surface temperatures. It's also closer to the sun than we are. So it had a lot of energy to trap. It did that super effectively. Okay. This is an example of a positive feedback. High temperatures made steam instead of water. What's the best greenhouse gas? Water vapor. So now you have the best greenhouse gas, okay, in your atmosphere, which causes more greenhouse. Okay, Higher temperatures mean more steam, so on and so forth. So you start by putting water vapor into the air, and you have no way of getting the water vapor out of the air. And the temperatures just keep going up and up and up until you get to 880 degrees. So this is the runaway greenhouse effect. So there's the atmosphere made out of like sulfuric acid, like we talked before. Sulfuric acid down here, that's all from the volcanoes. And then at the very bottom, you have a troposphere where the temperature is over here in the 700s. Okay, we're going to talk in more detail about Earth's climate and why we're trying to avoid this fate. But yeah, fun stuff, right? Okay. Sorry, folks online, that half of the lecture is not recorded. That's my bad. Next time, if you're not available, I don't know. I don't know how to fix that for next time. I will do my best to make sure that it is recorded. Or not recorded, that the audio is working.